All right, how's everybody's week going? Good? Okay, not okay? Okay. So to recap, last time we covered homogeneous solutions to linear time invariant systems. Okay, so this is the component of the solution that is dependent on the initial conditions, and we solved a few examples of LTI systems based on civil engineering systems. We looked at a structural system, and we showed how you could find the homogeneous solution for that system corresponding to some initial displacement. So we went through the process for finding the homogeneous solution, which we will review again today. Today, we are going to be looking at the complete solutions to LTI systems. So again, this is the solution that incorporates not only the initial conditions of the system, but also our input UT, which we've been alluding to, but we haven't solved the system with an input thus far. We will be doing that today. So we're going to be looking at complete solutions to LTI systems, and we're also going to be looking at convolution and how it relates to complete solutions to LTI dynamical systems. So who's heard of the term convolution before? Okay, what context, any other hands? Who's heard of the term convolution before? Three. What context have you heard convolution used in your previous studies or in your research?
There is one in computer vision, convolutional neural network.
Convolutional neural networks. So that'll be the place where many students hear this term. Jimmy, where have you heard of convolution before?
Like trying to get, I don't know what you call it, like the output of probability functions, you some input and the probability function, and you get an output.
Right. So so it's used in probability as well. So in particular, if you have two random variables that are independent, if you add those two random variables together, the PDF, the probability density function of those two random variables added together is, essentially what you get when you convolve their two individual PDFs. Okay, so convolution is used in probability. Has anyone else encountered convolution before? Sorry? Signals, right? So is this like a signal processing kind of application, right? So in this class, we're going to be talking about convolution and its role in dynamical systems. So it plays a role in LTI systems. So essentially, it plays a role in finding the particular solution. So the solution corresponding to some time series input to a dynamical system as well. So convolution is a really fascinating subject. I'm going to be covering it for the context of dynamical systems in particular, but it has many other applications, as you've noted. So I think it's a really important concept to learn in graduate school. It appears all over the place, and I'm going to give you a formal introduction to convolution today. Okay, are there any questions before I move on? No, we're good. Okay, so let's talk about the topic of today's lesson, complete solutions to LTI systems. Okay, so let's consider an LTI continuous time system. So note, when I say LTI system, I'm going to be talking specifically about dynamical systems. So when I use that term, I typically mean systems described by differential or difference equations. Okay, so just to be clear, LTI means a dynamical system in this class. So let's say we have our block diagram. We have a system. We have some input UT, and we have some output YT. So you know the drill at this point. And this system, a continuous time LTI system, is modeled by an ordinary differential equation. Okay, so this is just kind of a recap here. So let's just state the standard form of an LTI differential equation. So we have the nth derivative of y with respect to time plus a n minus 1, a constant, times the n minus 1th derivative of y with respect to time, and so on, plus a1 times dy dt plus a naught y is equal to u. Okay, so let's just say that there's a single input. We're not dealing with any of its derivatives. Okay, so this is our standard form for an LTI system. And for a given input, ut, our solution is given by the following expression. We have that our complete solution, yt, is equal to the homogeneous solution, which I'll call yh of t, plus the particular solution, which I'll call yp of t. Okay, so just to recap, can anyone tell me what the difference is between the homogeneous solution and the particular solution? So what does the homogeneous solution incorporate that the particular solution doesn't, and vice versa? So for the homogeneous solution, what does that incorporate? Right. So the homogeneous solution incorporates the response to the initial conditions, but it doesn't account for the input ut. And for the particular solution, it's the other way around. So the particular solution incorporates the response to the inputs to the system over time, but it doesn't incorporate the initial conditions of the system. Okay, so let me just write that down to recap. So this is the homogeneous solution. This is the particular solution. And adding them together, for a system that is linear, we can add those two together to get the complete solution. Okay, so because the system is linear, we can simply add up the responses independently from the homogeneous solution and the particular solution. Okay, so just to recap, this assumes y naught is not equal to 0. The particular solution, y naught equal to 0, but our input ut not equal to 0. Similarly, for the homogeneous solution, we assume ut equal to 0. Okay. So does anyone remember from undergraduate differential equations how the particular solution to an arbitrary input is found? Is this something that you covered in undergraduate differential equations? You did? So how did you find the particular solution to an ordinary differential equation?
I don't remember the general. Well, there's a few methods. I guess the one that I used most often was Laplace transform.
So Laplace transforms will do it. That is true. So I'm going to give you the method today in the time domain. This is the general method that will work for any input. Okay, so this is a general solution that'll work for any input. But to find the particular solution, what we're going to do we will apply convolution. Okay, so to find the particular solution, we will convolve the input ut with the system's impulse response function. Has anyone heard the term impulse response function? A couple of you? Okay, so this is a general solution procedure that'll work for any LTI system. It'll work in discrete time or continuous time. And I'll show you exactly how how it works. We'll go through what an impulse response function is. We'll go through convolution, what that is, and we'll work through a few examples. Okay, are there any questions before I move on? Okay, so first, just a show of hands, who's heard of the term impulse response function? Can I just see? Just one? Who's heard of the term Green's function? Okay, so you've heard of Green's function. Okay, so to talk about impulse response, we're first going to have to talk about what an impulsive input is. So we're going to be talking about impulsive inputs to LTI systems. Let me write this, impulsive inputs. And you can essentially think of an impulsive input is what's the response of the system to an instantaneous shock or an instantaneous input to the system. Okay, so we'll define this formally. So consider the impulsive input. And it'll look something like this. Okay, so we'll have a graph here. The y-axis is ut, the x-axis is t. And I'll draw a couple tick marks here. Okay, and the impulse input is defined as follows. It is 0 everywhere except for the origin. So it's 0 everywhere except for at time t equals 0. And we'll denote it by this little arrow, and I'll call it delta t. Okay, so it's 0 everywhere except for the origin, and I will define the properties of this function in a second. Okay, so we'll call this an impulse load. Our ut is equal to delta, okay, where delta t is a Dirac delta. Has anyone heard the term Dirac delta? Okay. Okay. Sorry? Okay. Okay. So Dirac delta is a kind of curious function that's defined as follows. It's actually not technically a function. Delta t is considered as infinity or infinite at t equals 0 and 0 everywhere else. Okay. So one way you can think of a Dirac delta is, let's say you have a normal distribution and you keep reducing the variance of that normal distribution such that your bell curve gets skinnier and taller until you get to a variance of 0. You'll arrive at a Dirac delta. And importantly, the integral of this function from negative infinity to positive infinity, we take the integral over time. This evaluates to 1. Okay, so it's a function that is 0 everywhere except for time equals 0, where it has a magnitude that you can consider as infinite. And if you integrate this function, it gives you 1, it gives you unity. Okay, are there any questions on the Dirac delta before I move forward? I know this is can kind of be an abstract concept and hard to think about. Any questions about this function before I move on? Okay, so you can think of this as an impulsive load to the dynamical systems that we've looked at so far. So for instance, if you have our structural system, and let's say you just whack the structural system with a hammer at the very first time step, you can consider that as an impulsive load to the system. Okay, it's a load that is instantaneous in time. Great. So an important property of the Dirac delta, this is a really important finding. If we assuming that some function f of t is continuous, then the integral, if we evaluate from time negative infinity to infinity of f tau delta t minus tau, where delta is our Dirac delta, d tau, this spits back out your function f at time t. Okay, so this is called the sifting property. Okay, this is called the sifting property of the Dirac delta. If we take the integral of a function times the Dirac delta, shifted by some time tau, we get back the function evaluated at time t. Okay, and this is a really important result because it means that any function f of t can be thought of as an infinite train of impulses. And I'll draw this out for you. Okay, so let me draw this out for you. Give you a second to write that down. Okay, so let's say we have some function f of t. There's a function of time, and it looks something like this. Okay, it's just some function, it can be anything. So we can think of this function as being composed of an infinite train of impulses. So let's just draw the envelope of this function here. And we can think of this function as being composed of all of these little Dirac deltas, such that when you integrate over them, it returns the original function. So you can decompose any function f of t into an infinite train of Dirac deltas, an infinite succession of Dirac deltas. And this gives a hint for how we might go about computing the response of a system to some arbitrary input ut. Okay, so think about this for a little bit. A couple of questions just to make you think. So I have here that there's all these little deltas, but they are different magnitudes. But I also told you that the Dirac delta has an infinite magnitude. So how can that be? Right. So essentially, it's kind of misleading to think of a Dirac delta as having an infinite magnitude. The important point is that when you integrate it over some time interval, it returns unity, right? So you can have this expression, the integral of delta t dt is equal to 1, right? But we could scale this by some amount. So we could, scale this. We could evaluate, 1/2 delta t, and then the right-hand side would be 1/2, right? So really, we're talking about what's the integral of our Dirac delta over some interval, right? Okay. And note that in discrete time also, there's an analogous delta that is finite. So for discrete time systems, delta is defined a little bit differently. Okay. Great. Okay, so keep that in the back of your mind. Okay, now we're going to go into the definition of convolution. Okay, so we have a function f of t that we can equate to an infinite train of impulses. So now we're going to talk about convolution and the impulse response. Okay. So consider an input to an LTI system, UT. Okay, and if UT is continuous, we can represent it as an infinite train of impulses. Okay, so the key idea is that each impulse has a response. So each impulse has some response. So if we hit the system with delta t evaluated at t minus tau, this will give us some response h of t minus tau. Okay, and we'll call the response to an impulse the impulse response. Okay, so each of those impulses is going to give us some response ht minus tau. And by superposition, the response to the entire signal ut is given by convolving the input with our impulse response. So let me write this out. By superposition, and I'll make this more clear with a drawing in a second. So by superposition, the response to an input ut is given by the convolution integral which is defined as follows. The particular solution, which is the response to some input ut, is given by the integral from -infinity to infinity of u tau, that's our input, times h t minus tau d tau. Okay, or alternatively, and I know this will be confusing for a second, but I'm going to draw a picture to make this more clear. The particular solution, we can change the arguments u t minus tau h tau. These are both equivalent. Okay, so this operation here is called convolution. So let me draw a picture to help clarify things. Okay, so the key idea is that each of those impulsive inputs produces some impulse response h of t, right? And when we're applying the input to the system, we're essentially going through and we're hitting the system with each one of those scaled impulses, finding the response for each of them, and then adding them all together or integrating them in the continuous case. So let me draw a quick picture to demonstrate. Okay, let's see here. Just want to make sure I have enough space. Okay, I'm going to draw a couple plots for you here. Let me give a little bit space there. Okay, so for each of these, on the left, we're going to have our input. So this will be UT, UT, ut. On the right, we will have our output. So this will be yt, 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 and these are all functions of time, t, 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 t. So the key idea here is, let's say we hit our system with a impulsive input at time 0. Okay, it'll produce some output h of t. Okay, so let's just say it looks something like that. Let's say we have some sort of second order system where we get this little oscillation here. Okay, so this response to the system to some impulsive input we call h of t, which is the impulse response. You can think of this as kind of the a function that is kind of a kernel of the system. And so it describes the system's output to an instantaneous load, an instantaneous input. Okay, now let's say we shift. So this is delta t. This is our Dirac delta at the origin. Let's say we shift our input. Actually, let's make it smaller as well. Let's shift our input so that we have delta t minus tau, and I'm just going to say it's 1/2. Okay, so this will also produce a response. Okay, shifted like so, and scaled. So we'll end up with something like 1/2 h t minus tau. Okay, so we applied a Dirac delta to the system, an impulsive load to the system at time 0, it produces some impulse response. If we shift that impulsive load and scale it, we'll get a shifted and scaled impulse response. Okay, so then let's say we have some function that we can decompose into a train of Dirac deltas. Something like this. And we run each one of those through the system. So let me just make it clear that this is being run through our system. In this case, we will get h of t corresponding to the first Dirac delta, some shifted and scaled h of t corresponding to the second Dirac delta, some shifted and scaled h of t corresponding to the third Dirac delta, and so on. Let's just kind of finish off here. Okay, and the ultimate response that we get to the system will essentially be what we get if we add up or integrate all of these individual responses together. Okay, are there any questions about this concept before I move on? Any questions about impulse response? Has anyone encountered this concept before in undergraduate differential equations? Has anyone encountered the concept of a impulse response? Okay, this is an extremely important subject. It will kind of form the basis for how we talk about responses to inputs over the course of the semester. So this is, it's not, I just want to make it clear that it's not something that should be addressed in half a lecture and never touched again. This is extremely important because what it means is for an LTI system, you can essentially figure out what the response to that system is going to be to any input by characterizing its impulse response. So often what will be done, this will actually be done experimentally, in maybe a structures lab or something. Like they will actually go and hit the structure with a hammer, measure its response, and try to figure out what the impulse response is so that they can then know, well, what's its response going to be to a time series of an earthquake forcing, right? So the idea is you characterize the system's impulse response, and from that little kernel that describes the system's response to an impulsive input, you can evaluate the response to any arbitrary input. Okay, so it's a very important concept. Okay. Sorry? Oh, tau? Yeah, so whenever we have a function evaluated at t minus tau, that means we're shifting the function by tau to the right. So I'll write that out explicitly here. This is at time tau now. So for any function, if we evaluate that function at t minus tau, that's equivalent to shifting the original function by tau to the right. Okay, so good question. And I'm glad you pointed that out. Okay, so to summarize, okay, if you know the impulse response h of t, then for any continuous input, which I'll write as ut, the system response is given by yp of t, particular solution is equal to the integral from negative infinity to positive infinity of u tau, that's our input, h t minus tau, d tau. And again, just to be clear, this is our input. We're convolving it with our impulse response. And this operation inside the integral, this is called a convolution integral. So when people talk about convolution as in convolutional neural networks, this is exactly the same thing. Okay. Often this will be expressed as follows. So you'll often see convolution represented using the following notation: ut star h of t. Okay, so you'll often see this notation used for convolution as well. Okay. And so remember, this is only the particular solution. In order to find the complete solution, you have to add this to the homogeneous solution. So know that for the homework. Okay. Are there any questions before I move on? I'm going to give you a couple examples. Okay. So today I'm going to talk about using this operation to solve dynamical systems in the time domain. As Jimmy mentioned, you can also use the Laplace transform to solve for the particular solution, and that's what I'm going to be covering in next class. So there'll be a relation between what I showed you today and the Laplace transform, which I'll be showing you next time. That will explain why you use Laplace transforms if it was not explained to you in previous classes. Okay. Great. All right, so let's take a look at a couple examples. I'm going to go through a first order system, and I'm going to go through a second order system, and we're going to show how we can compute the complete solution for each one of these. Okay, so I'm going to go back to an electrical example first. Let's look at an example of a power grid under a constant voltage input. And we have a power grid. Let me just draw it out first. We have a power grid, which we're going to represent as a RC circuit. So we'll have a resistor. And we have some storage element in our power grid. Maybe it's like a battery or something. We'll just represent it as a capacitor. Okay, so we have a power grid that's going to be evaluated under a constant voltage input. So the voltage input to the system will be 100 volts. The resistance of the power grid, just in bulk, we'll treat this as a single resistor with a resistance of 1 mega ohm. And the storage element we'll treat as having a capacitance of 0.2 microfarads. Okay, so for this system, to be clear, our input is a voltage input, and this is a constant input of 100 volts. Okay, our output that we're interested in is the voltage across the storage element. Voltage across the storage element, which I'm going to denote as VC of t. Okay, so our input is the voltage input to the system. Our output that we're interested in is the voltage across the storage element. And we also have an initial condition that we need to account for. So the initial voltage across the storage element at time 0 is equal to 5 volts. Okay, so let's go ahead and first formulate a LTI system to describe the dynamics of this power grid system. And then we're going to find the homogeneous solution. And finally, we're going to find the particular solution. And from that, we can get the complete solution describing the behavior of this system. Okay, so to start, we can start solving the system by applying Kirchhoff's laws, right? So from Kirchhoff's voltage law, what does that tell us? So Kirchhoff's voltage law tells us that the sum of the voltage changes around each loop is equal to 0. So how can we write that mathematically? Let's go around each one of these elements. So we have, starting at this element, we have V of t, okay, minus the voltage drop across the resistor. So what's the voltage drop across the resistor? Yeah, current times the resistance. So that'll be, I'll just write the current as IRT and the resistance as R, minus the voltage change across this capacitor. So that'll be VC of t. That's our output that we're interested in. Okay, and we set this equal to 0. Okay. And for convenience here, I am going to rearrange this, and you'll see why a little bit later. So I'm going to rearrange this in terms of the current IR of t. We can just algebraically rearrange this here, and we get VT, the voltage input, minus VC of t, the capacitor voltage, over R. Okay, so save this for later. Okay. Does anyone remember now what's the expression that relates the current and voltage across a capacitor? So that would be for the resistor. For the capacitor? Right. So this is an equation just that I gave you from a previous lecture, but we have from that lecture that the capacitor dynamics. So this isn't something I expect you to memorize, but the capacitor dynamics are described by the following relation. The current through the capacitor is equal to the capacitance times the derivative of the voltage across the capacitor with respect to time. Okay, so we have an expression for the current in the capacitor and an expression for the current through the resistor. Okay. Now we can apply Kirchhoff's current law. And what does Kirchhoff's current law tell us about the relationship between the current through the capacitor and the current through the resistor? So they'll be the same, right? Because if, as we're going around the loop, the current through one element can't be less than or more than the current through another element. So we have that the current through the resistor is equal to the current through the capacitor. Okay, so let's go in and substitute these expressions for the current through the resistor and the current through the capacitor. From the previous page, we have this expression for the current through the resistor in terms of the input voltage and the voltage across the capacitor. So let's plug that in. We get VT minus VC of t over R is equal to C dVC by dt. Okay, so now we are in luck. We have an expression that relates the input and the output of the system. So let's rearrange this so that we have the input on one side and the output on the other side. So let's put the output, the capacitor voltage over on the left-hand side, and we get dVCT. It's kind of a tongue twister. dVCT by dt plus 1 over RC VCT. This is kind of funny to say, is equal to 1 over RC VT. Okay, so VT here being the input to our system, the input voltage, VCT being the output, which is the voltage across the capacitor. Okay, so we have a expression for our dynamical system. All right, so great. So now what we're going to do is we're going to find the complete solution to the system. So we need to find both the homogeneous solution as well as the particular solution, right? So first, let's go and just do what we're familiar with. Let's find the homogeneous solution. Okay, so we have our equation. I'm just going to write this out again. dVC by dt plus 1 over RC VCT is equal to 1 over RC VT, right? Okay, so for the homogeneous solution, what can we do here? Right, so first for the homogeneous solution, what can we do with this term here? Yeah, right. We don't need to consider the input to the system. So we have that dVCT by dt plus 1 over RC VCT is equal to 0. Okay, so as you mentioned, we can move this term over to the right-hand side. So we get dVCT by dt is equal to -1 over RC VC of t. Okay. Now, how can we solve this? Right. So essentially, we know what the system is, right? We've seen this multiple times now. So we can think of this as just being some system dx by dt is equal to ax, right? What's the solution to a system of this form? Right. So this will be e to the at x naught, right? So that is the homogeneous solution. You can just look at this problem and see the solution for the homogeneous case is going to be Vc of t is equal to e to the -1 over RC t times the initial voltage across the capacitor. So this is our homogeneous solution. Okay, so that was pretty quick. Okay, cool. So yeah, that wasn't bad at all. Oh, I should write, let me just be clear. This is just the homogeneous part. So I'm going to write VCH of t. So this is the homogeneous component of the solution. All right, now let's go for the particular solution. How can we do this? All right. So from our discussion before, we know that the particular solution is equal to the convolution integral of our impulse response function ht minus tau with our input u tau d tau. Actually, let me write this as v instead of u because I used v for the other variable. Okay. Now the question here is, we know what the input is. It's a constant, right? That's from the problem statement. What about the impulse response? How do we get this? Well, in truth, we can't really get it yet. I will show you how to get the impulse response. I'll show you a method to determine the impulse response in the next class when we cover Laplace transforms. But for now, I will kind of give you the following argument to think about how we can get the impulse response for this system. So this isn't going to be a formal method. This is more of a conceptual argument for how we can obtain the impulse response in this case. Okay, so let's say we have our system dvct by dt plus 1 over RC vct is equal to 1 over RC. And the input to the system, if we're looking for the impulse response, will be what? The Dirac delta, right? Okay, so one way to think about the system, and just to be clear, for the particular solution, VC at time 0 is going to, we're going to consider it as 0. So one way to think about the impulse response is you can think of it as being equivalent to determining the response to the system for an initial condition. Okay, so if we treat the impulse to the system, you can model the response of the system to an initial condition using an impulse defined at the origin at time step t equal to 0. So what we're going to do here is we're going to find an initial condition to the system that produces a homogeneous response that's equivalent to the impulse response. Okay, so let's say we have this system, we have that the initial voltage to the system is 0. Let's integrate this system with respect to time, and let's integrate it from the negative side of 0 to the positive side of 0. So note that I'm kind of abusing some concepts here, but it'll work out for us. So we're integrating dVc plus the second expression here, 1 over RC VCT dt is equal to 1 over RC integral from 0 minus to 0 plus delta t dt. Okay, so if we evaluate this expression, first of all, what does the term inside this integral become from the definition of the Dirac delta? 1. Okay, and if we're integrating VCT over 0, so from the negative side of 0 to the positive side of 0, what does this integral evaluate to? Which is 0, right? Okay, and so what we end up with is that the impulse response or the impulsive input is equivalent to starting with an initial condition, VC of 0, equal to 1 over RC, right? And that comes from this 1 over RC here. So you can think of the impulse response as being equivalent to the response of the system to some initial condition in this case. Okay, so with that, let's just write out our impulse response. So the impulse response is equivalent to the response to the homogeneous response for an initial condition of VC equal to 1 over RC. So what is the equation for our impulse response? Let's go back to the homogeneous solution. So what will the expression for our impulse response be if it's equivalent to evaluating the homogeneous solution at VC of 0 equal to 1 over RC? Right. We just substitute 1 over RC into this expression, and that will give us our impulse response. Okay, so our H of t is equal to 1 over RC e to the negative 1 over RC t. Okay, and now what do we do to find the particular solution? We integrate, right? Oh, but a special kind of integrate. How do we integrate, or what are we integrating here? So for the particular solution, what do we need to do to compute the response? Right, we're computing the convolution integral, right? So we're convolving ht minus tau, u tau, d tau. And this will be equal to, so for our h of t minus tau, this will be 1 over RC e to the negative 1 over RC t minus tau. And what is our ut here? So it'll be our input to the system, right? So let's just call it V. And so we don't have to deal with numbers flying around. Let's just call this V, 100 volts. And note here that this voltage input, I didn't specify it here, but this is applied at time 0 to infinity. Okay, so for the limits of our integration, if we want to find the particular solution at time t, we can integrate this from 0 to t. Okay, and our ut here will be just V, our input, constant input voltage. Okay, integrated over d tau. All right, so let's simplify this a bit. Let's pull the constant terms out of the integral. So we have V over RC, and the integral from 0 to t of e to the negative 1 over RC t minus tau d tau. Okay, and how can we simplify this problem even further, just to make it really easy? Right, so we can split up this exponential term to get rid of the term that doesn't depend on tau, which is the variable we're integrating over. So you might have done this in homework 1. Okay, so just advancing forward here, we have VCP. So we took it out of the integral. So we have e to the negative 1 over RCT, all times the integral 0 to t of e to the 1 over RC. So note the negative is not there anymore. E to the 1 over RC tau d tau. Okay. And what is the indefinite integral of e to the 1 over RC tau? Yes, I think I heard it, but let me just, so what is the integral of this function here? Great, so it'll be RC e to the 1 over RC t evaluated from t to 0. Okay. So from this we get, let's just keep simplifying it, v over RC e to the negative 1 over RC t, and inside this expression we have RC e to the 1 over RC t minus RC e to the 0, right? Okay, so this here becomes 1. And if we combine these expressions, we get, okay, so these two RCs cancel out. We get V e to the negative 1 over RC t plus 1 over RC t. Okay, so this expression here evaluates to 0 minus V, right? Oh, sorry, V e to the negative 1 over RCT. Okay, and if we simplify this more, we can get V times 1 minus e to the negative 1 over RCT. Okay, so that is the particular solution to a constant voltage input. Does this look familiar to anybody? Did anyone use this method in undergrad? to solve particular solutions? No? Oh, well, I guess you learned something new today. Cool. So this is the general solution procedure. And note, importantly, if you have an input to the system that can't be described analytically, you can find the response to the system by numerically integrating with the convolution integral. So if your UT can't be described analytically, you find the particular solution by numerically integrating, okay? Okay, so are we done? No. So what do we need to do to find the complete solution? Okay, so we have to add them both together. So the complete solution is given by y is equal to yh plus yp. So we have to add the homogeneous and particular parts together. In this case, our VC of t is equal to the homogeneous solution. So that's e to the negative 1 over RCT times VC 0 plus our expression for the particular solution, which was V1 minus e to the negative 1 over RCT. Okay, and we can rearrange this to group all the exponential terms together, and we get e to the negative 1 over RCT times VC0, so the initial condition, minus V, all plus V, our voltage input. So let's substitute our values for the initial condition and RC, and what we get is the following expression. The capacitor voltage over time is equal to 100 minus 95 times e to the negative 5t. Okay. So that was a lot of work, but that's how you find the response of the system to some arbitrary input, is by convolving with the impulse response function. Okay, so just to quickly plot the result, what we'll see is something like this. This is VC over t, and this is time. What the response of the system will look like. So this is the response to what's called a step input. So it's often called a step input or a Heaviside function. It's just a constant input that starts at time 0. You'll get that the system starts with an initial voltage. So this is 5 volts, and it rises up and approaches this final voltage of 100 volts. Okay, so that is what the response of the system will look like. Great. Okay, are there any questions on this procedure before I move on? Any questions? Great. So yes, that is the general solution procedure. It'll work for any input you give it. Okay, let's take a look now at a little bit more complicated of an example. And I don't know if I'm going to be able to get through this completely, but let's take a look at our structural system. Let's look at the response of a second order system. Okay, and this is the complete solution. All right, so let's say we have a structure just like before. And our structure has some mass M. It has stiffness, it has damping. And it has a force that's applied to it, which we'll call F of t. And that force induces a displacement, which we will call X of t. Okay, so we know the drill at this point. The dynamics of the system can be expressed via Newton's second law. Mx double dot plus Cx dot plus Kx is equal to F, our input forcing. Let's go ahead and monetize the system. So we divide by M, and we get X double dot plus C over M, X dot plus k over m x is equal to 1 over m times the input force. Okay, so what I'm going to do is I'm going to take this system and I'm going to write it in a slightly different form that will make it easier to analyze later. You may have seen this in undergraduate differential equations, but I'm going to take this system here and I'm going to redefine it as follows. X double dot plus 2 zeta omega n times x dot plus omega n squared x is equal to 1 over m f. Okay, where omega n is equal to the square root of k over m, so our stiffness over our mass, and this is called the natural frequency. So you may have heard these terms from undergraduate differential equations. Our zeta is our damping ratio, and that's equal to C over CR. So this is the damping over the critical damping. So this is called the damping ratio. And I want to introduce this notation because it'll appear later. And CR, this is the critical damping. This is equal to 2 times the mass times the natural frequency. So this is the critical damping. This will appear a lot in controls literature. Okay, and just to be clear, omega n squared is equal to k over m. So I've substituted that in here for k over m. And 2 zeta omega n is equal to the damping coefficient over the mass. Okay, so who's seen these terms before? Okay, you've seen these terms. Anyone seen these terms from undergraduate differential equations or physics? Okay, great. So let's go ahead and compute the homogeneous solution. So we're going to compute the homogeneous solution and then the particular solution. We looked at this system previously, but we only computed the homogeneous solution for the case with an initial displacement, but no initial velocity. So we're gonna go ahead and compute the general case here. So let's look at the homogeneous case. Okay, so we have that our system is described by x double dot plus, 2 zeta omega n x dot plus omega n squared x is equal to 0 for the homogeneous case. Okay, and let's compute the roots of this. Let's compute the roots of the characteristic polynomial. So what are the roots? Anyone tell me? So so we have negative b plus or minus square root of b squared minus 4ac over 2a. So let's go ahead and fill in each of these terms. What's the first term here? Yeah, so it'll be negative 2 zeta omega n. Okay. Plus or minus. Okay. Right. So this will be 4 zeta squared omega n squared. Very good. Okay. Minus 4. Our a is 1 and our c is omega squared. Okay, so we have okay, that for the numerator, and for the denominator, our a is 1, so our denominator will be 2. Okay, so from here you can probably see why the form we put it in will be useful. So these 2's here divide out, so we'll get negative zeta times the natural frequency plus or minus. And let's look at this expression here. Okay, so this 4, this factors out, becomes 2 outside of the square root, and that divides out. The omega n appears in both terms. So what we can do is we can rewrite this as zeta squared minus 1 and move the natural frequency outside of the square root. So we have omega n times square root of zeta squared minus 1. Okay. Now let's rearrange this a little bit more. Let's assume that we can just let's write this second part in terms of the imaginary unit. So we can factor out a -1 from this square root, and we get j times omega n 1 minus zeta squared. And what I'm going to do just for convenience is this whole thing here, I'm going to define this as omega d. Let's just call it omega d. So omega d is equal to the natural frequency times the square root of 1 minus zeta squared. That is too small to write that over there. Okay. Let me put it somewhere else. So omega d is equal to natural frequency times 1 minus zeta squared. Okay, and so we can write the roots as follows. This is equal to negative zeta times the natural frequency plus or minus j omega d. Okay, so this here will be the real part. And this here will be the imaginary part of our root. So we have it in this convenient form for us to use. Okay. All right, looks like I'm probably going to run out of time today, but let's just keep going for a little bit longer. So we have that our prototype solution for any second order system will be of the following form: e to the at times c1 cosine bt plus c2 sine bt. And as before, we have to determine the coefficients c1 and c2. So let's just write out, so can we fill in these a and b variables real quick? Just to help me out here. So we have e to the, okay, great, minus zeta omega nt times c1 cosine of omega d, very good, times t plus c2 sine of omega dt. Okay, so wow. So that form we wrote it in makes it a lot more convenient to write. Let's go ahead and find C1. Okay, so how do we do this again? Right, we apply our initial conditions. So let's apply the initial condition for the displacement first. What we end up with, if we substitute in 0 for t in this expression, we get e to the negative zeta omega n times 0 times c1 cosine of 0 plus c2 sine of 0. Okay, what happens to this term here? Goes to 1. This term here, 1. This term here, 0. Very good. Okay, and so what we end up with is c1 is equal to x0. Okay, very good. So that's just kind of a review of what we did last time. Let's find c2 now. How much time do I have here? Got a couple minutes. All right. So the first thing we have to do is we have to differentiate this expression here. So we can apply the product rule. And we get that x dot of t is equal to negative zeta omega n e to the negative zeta omega nt times x0 cosine omega dt. So I've substituted in c1 here, plus c2 sine omega dt. Okay, and then plus our other term in the product rule, which will be e to the negative zeta omega nt times, we differentiate each one of these, and we get negative x times 0 times omega d sine omega dt plus C2 times omega d times cosine omega d t. Oh gosh, I ran out of space. Times cosine omega dt. Okay, so let's go ahead and evaluate this at time equal to 0. So I'm just going to go ahead and evaluate this at 0. This here becomes 1, right? This here, this becomes, sorry, this becomes 1. This becomes 0. Okay, what about this term here? This becomes 1. This becomes 0. And this becomes 1, right? And so we can simplify this. And what we end up with is x dot 0 is equal to negative zeta times the natural frequency times the initial displacement x0 plus C2 omega d. And thus C2 is equal to x dot 0 plus zeta times the natural frequency times the initial displacement all over omega d. All right, and so we can write out the general homogeneous solution. So I'm going to go ahead and do that. So this isn't in the type notes, so let me just make sure I have this for you. Our homogeneous solution is given by e to the negative zeta times the natural frequency times time, all times x0, our initial displacement, times cosine omega dt, plus x dot 0, our initial velocity, plus zeta omega n, our natural frequency, times our initial displacement, all over omega d, times sine of omega dt. Okay, so this is our general homogeneous solution. Okay, so I don't have time to go through the particular solution, but essentially we can follow a similar argument for the particular solution as we did for the RC circuit case, and we can treat the impulse response to the system as being equivalent to having some initial velocity in the system, so or an initial momentum, unit momentum input to the system. So I will go ahead and stop there for today. I will have to pick this up on Thursday, where we'll finish off this example quickly and then move on to Laplace transforms. But I want to respect your time here, so that's it for today. And I will go ahead and stop here.